Okay, so I do want to start by thanking the FAA for hosting us. We've been very lucky in the last few meetings to have some really nice facilities, and that's been great for us. And thanks to Wing, we will have a demo on Wednesday, and we're still kind of working logistics of that, so we'll get that sort of all figured out. I'll go over the agenda in a moment, but we've sort of got now a tradition, and we've been together long enough to actually sort of have a tradition, which is nice, of doing a quick around the room introduction, just your name, where you're from, maybe a couple sentences on your interests and that kind of thing. We'll start over here with Andy.
I'm Andy Lasher. I'm with NASA Langley. I'm the Chief Technologist for Future Aerospace Operations at Langley, and I'm also leading one of the subgroups on aerospace integration.
Hi, my name is Shrikant, and I'm an Associate Professor of Aerospace Engineering at St. Louis University. I teach classes on flight dynamics and controls, and my research interests are in uncrewed systems. All problems.
I'm Barry Sullivan. I'm with NASA's Aerospace Operations Safety Program Office. I'm a technical integration manager. We oversee a system-wide safety project, Air Mobility Pathfinders project, Air Traffic Management Exploration, and ACERO, which is Advanced Capabilities for Emergency Response Operations.
Morning, guys. Scott Shell with AJEP Design Works, and I'm one of the co-leads from the Small UAS Working Group. We'll be giving a discussion after Andy's discussion is up.
Hi everyone, my name is Radhika. I'm a PhD candidate in aviation factors at Purdue University, and I'm working on characterizing and assessing crew resident performance for airborne operations.
So I'm Nelson Brown. I'm from NASA Armstrong, and I'm part of the TQ project. But I'm the PI for a small activity that's collecting video data for training autonomous systems.
Benjamin Hargis. I work at NASA Langley. I am also with TQ, and I lead the technical effort in a program developing a low fidelity simulation for autonomy in airspace.
Hi, I'm from Mobile. I'm also from NASA Langley. I actually work under him as just one of the technical researchers.
I'm Sam Emerson. I'm from a group called Actima. I'm a research scientist with a background in cognitive psychology. Jay is, as you guys probably know, retiring soon. So big boots to fill, but they had to hire a whole team to replace him. So we'll be taking the torch as Jay starts to phase out.
I'm Kara Orbis. I'm with Optima as well. My background is actually industrial organizational psychology, but our company obviously does a lot of research in this area. Happy to be here and looking forward to being here with that.
Hi everyone, this is Yuki from PwC. We're currently under the government-funded project regarding integration. Some of the considerations and ideas could be brought up and discuss more about potential requirements for the integration. Japan CEO. Thank you. So hosting the videos from NASA Ames, so I'm called. So I also lead some system things on the TQ from autonomy metrics and measures. So working with this group, very interested in specific metrics for general operations.
Tim Ligley from General Atomics and Aeronautical Systems. I'm our technical lead for airspace integration, so I'm involved in developing deployed technologies and everything else that's needed to integrate large UAS into civil airspace.
Hi, Sienna Whiteside. I am the project manager for revolutionary aviation mobility at NASA under the TQ project that a lot of people have mentioned, and end-to-end is a big portion of that portfolio. I am new in the role as of about 6 months ago. Vanessa Aubuchon was the previous person in that role, and so my background is mostly in conceptual design analysis of advanced air mobility vehicles side, so learning a lot about the airspace.
We are getting set.
Yes, we are. Sorry, go ahead. Leon San, associate professor in Baylor. My research area is vehicle operations. currently working on a NASA-funded project. It's glad to be here.
Good morning, everybody. My name is George Gorosky. I'm the technical lead for the Autonomous Systems discipline within the Transformative Tools and Technologies project. Again, for everybody, the multi-vehicle end-to-end working group is one of the 9 activities in my research portfolio. I'm really, really happy that you all made time to attend this meeting. I think we're gonna have a really great 3 days, see some cool stuff, and also more importantly, get your voice heard within this dialogue that we're having, because we're really moving the rock down the road. Thank you.
Eric Chansey, NASA Langley. I lead a group that looks at human autonomy teaming. Been interested in the end-to-end concept for a while now. Hear a little bit more about that later this week.
I'm Ali Biltikoff. I'm also at NASA Langley. I work with Eric and Mike under the GQ project. We're in some project. So I'm very excited to be my first one.
Hi, Garrett Sadler. I'm a human factor researcher from NASA Ames Research Center in the Human Autonomy Teaming Lab. And together with Scott Sheff, one of the leads of the small UAS working group, although Scott probably deserves 90% of all the credit there. And also together with my colleague Megan Sepan, who is not able to be here this week with us, but I'm a lead for one of the activities of the 9 that George was talking about on end-to-end operations.
Summer Brandt, NASA Ames, Deputy Project Manager for System-Wide Safety. So we're looking at, one of the things that we looked at is inventory of vehicles and operations is what kind of capabilities are required for safety lines. Also, co-lead for the Human Autonomy Teaming Lab with Garrett Sadler, the background is human factors.
Will Scavanja, Chief Engineer for Aircraft Systems at Dronout, and focuses on making sure aircraft never fall from the sky.
My name is Mark. I'm here. I'm an associate professor at Embry-Riddle Aeronautical University, and I'm interested in end-to-end vehicle simulation and testing. And Sang is here also.
Yeah, I'm a PhD student from Embry-Riddle as well. I multi-L1 agents and also multi-agent in terms of vehicles. So it's like double mass.
I'm Mike Florowitz from NASA Langley. I am the Langley Point Project Autonomous Systems Discipline in the TQ project, so I help George manage that portfolio. And then I also co-lead the Human Autonomy Teaming foundational research activity.
He's right there.
No, go ahead.
Okay. I'm Mark Blanks. I'm the head of global flight operations for Wing. A day job. We operate end-to-end daily, so very interested in this topic. My night and weekend job is in the chair of the ASTM F38 committee on UAS.
Tim, you.
Okay. We got one more here.
Oh,
yeah.
Oh, we're doing introduction now.
Oh, hello. Faisal Omar, NASA Ames, and my role on the Associate Project Manager for everything.
Tim Bigelow, I'm with the FAA. I'm your host for this facility today. I'm actually out of headquarters, and I'm with AFS 700. That will be on the next presentation because I will be explaining who we are, what we do. I'm a project manager, and I'm also the head of our lead for commercial or air carrier operations, carrying packages for people who need one.
Everyone, I'm Jonathan Nguyen, and I am part of NARI, that's the NASA Aeronautics Research Institute, and I'm the lead coordinator for this working group. So I've been spamming everyone's inbox, and maybe they got through, so everyone's here. Yeah, making sure everything runs smoothly and everyone's well caffeinated.
We're just doing introductions, if you want to. Yeah.
The only one who wasn't introduced.
Yeah.
I'm Brian Betty from NASA Langley, and I'm working on the ETMD project.
Okay, thanks everybody for coming. I really appreciate it. Jonathan and Tim, thank you guys for really helping get this thing set up. We'll go through the agenda really quickly. The idea for this meeting was really that, I think about a year ago, at NASA Langley, we got together and came up with 3 main topics that we wanted to write white papers on. And those are the evaluation methodologies, interventions or exceptions, and then airspace integration. And we've been working on those in various different ways over the course of the last year. And we wanted to kind of get together and give you a status of where we are. They, you know, spoiler alert, they are not completely done and ready to publish, but they have gotten a good start. And so we will we'll go through and discuss those. And in a moment, Mike will talk about where and how we're going to publish these as we move forward. In addition to those 3 areas, the small UAS group that we tried to kill wouldn't die is also writing a white paper, and yours might even be farther along. So we have a chance to hear what they've been working on as well later in the week. And so that's what we're going to talk about today, where we're going to publish it, evaluations, interventions, integration, and the small UAS, and then we're pretty much done and have some free time. We can decide what we're going to do there. I think Jonathan has been talking about setting up a happy hour today. You have a slide on that? Yeah. You don't have to bring it up right now, but. So there's nothing formal there, right? We just kind of show up, right?
Yeah, nothing formal.
Yeah. So this is at the Truck Yard Beer Garden. Very close to our Hyatt Hotel. I don't know where other folks are staying, but not too far away. So we're saying meet up there around 7 o'clock and have a beer.
So 7 o'clock is when happy hour ends. Actually, directly after this meeting ends.
So right after this meeting until 7-ish or something.
Yeah, until 7 o'clock. That's when happy hour. But feel free to.
Oh, until. I guess if I actually read it. Part of my process.
Whatever you decide to do.
So everybody's invited, obviously, and hope to see you over there for having a beer. Okay, go back to the agenda. So this is day 1. Let's go to day 2. So day 2, the idea is demos in the morning. We've been able to work with Mark and Tim and try to set up some demos with Wing, showing us their BVLOS operations. And we have to get together and discuss that a little bit this morning to get all the logistics together. It might be a little bit farther drive than we had thought. So we'll be encouraging people to carpool. And hopefully we will be able to get done back here by 1:30. Mark, do you think that's reasonable? Okay, so we'll give that a try. And then when we get back after the demos, which I think should be fun, we have Fabrice Kunze, who's not at SkyGrid anymore. He's now at Avidyne as president, CEO of Avidyne. So he'll be talking. We have Pham Trung from the FAA talking about the FAA AI roadmap, which I think will be really interesting. I'm going to spend a few minutes talking about meaningful human control of AI-based systems, which is a topic that I worked with a NATO group to develop a technical memo that will be out any day now and goes along nicely with the AI. And then Tim will talk about FAA certifications, kind of where we are with that. And then we have a nice presentation from Zipline, who's been doing a lot of this kind of work over in Africa for some time. And here, yeah, that's right. So that's day 2, and then day 3. Basically, we've got a couple of studies in the morning. When we started this group a few years ago, part of the idea was for it to inform NASA labs about the important aspects of things that they ought to be looking at that would help benefit the whole community. And so now we're getting into a little bit of a feedback loop from NASA Langley and then NASA Ames on some experiments that they have run and have planned, and to get feedback from you guys on what they're working on there. So I think it's kind of a nice full circle kind of thing. And then given that we are at a place where we've completed, we haven't completed these white papers. We will be completing these white papers. The question becomes kind of, where do we go from here? What's this group can this group do to really help the community move forward? And so we're going to try to look at that from a couple different places. One is an industry forum asking industry what would be most useful for them from this kind of meeting. And then the other one is a government forum, talking to folks from different NASA organizations and the FAA, and how they can incorporate this into the work that they're doing. So I think that'll be helpful in getting some ideas about moving this forward. And then, as mentioned earlier, Aptima is going to be taking over a lot of this role, and Samantha will introduce herself and talk to you about ways going forward. Okay, that's all of that. Any questions, comments? Okay, I think Tim, you are up.
I'll make this quick. I see I've got 4 minutes to accomplish my 25-minute program.
Take your time. We've got plenty of time.
Not a problem. For those that like to hide behind the podium, it is here. I am not one. I like to be a moving target. It's harder to hit that way. I work for the FAA, so remember, I'm not happy till you're not happy. That was always our old Actually, we use the term that we're here to help you. So I'm with the FAA. I'm actually with headquarters. I am not in the region. I did spend time in the region and all. Yes, okay. So the big thing that I wanted to cover today was my boss was going to come today and talk about AFS 700. What does that mean to y'all? Well, that's going to mean a lot to you right now. AFS 700 is the Emerging Divisions Technology. It's broken into 6 branches. Okay? It just started as of a year ago. We actually began October 1st of 2023. They went into all the different divisions and headquarters that are working on different projects and finding out who's doing anything with UAS, unmanned aircraft, advanced technology. And they brought us all together and they said, hey, we're going to start a new division. Would you like to come to it? They only wanted the people that wanted to still do this stuff. Because what we found was before that, I was in AFS 200, which is an air carrier division. We specialize in all the Part 135 and 121 airlines, okay? Well, that's great, except for the fact that we were doing UAS in there, and a lot of the experienced pilots, we'll say that way, you're like, yeah, those are toys. You don't care about those things. And they didn't want spending time with them. They didn't want to talk about it. And when you set stuff up through our division managers, sometimes got a little lost because divisions were talking to different divisions. So that's when they said, no, no more. Because moving technology is moving so quickly, we got to put it all under one division. This way, only one manager, Joe Mora, is our division manager, has final say on whether we can move forward with a project or not. This sped things up greatly of what we were accomplishing. So out of the 6 divisions, the first one is 710. That is our maintenance division. Anybody that has to deal with maintenance of an aircraft, that's your airworthiness, like the A&Ps that work on aircraft or might be working on aircraft, that's 710. 720 is our evaluations division. Anytime we have a new type of aircraft, new piece of equipment that needs to be evaluated, so they can, this is the team that will send out people and they'll take a look at the equipment and say, yes, you can use this in this operation. But if you use it, they're going to look at it beyond that and they're going to say, if you use it, here's things you need to consider. Are we willing to do this? For example, C2. Everyone's heard of C2, command and control. They're the ones looking at C2 and they're saying, well, okay, what happens if you lose a cell tower? A company's using cell towers. What if they're using radio frequencies? What's going to happen when they lose that radio frequency and they're working with an unmanned aircraft? They're the ones kind of leading the way in that. What does the pilot control station, this is our biggest topic lately, what does a pilot control station need to have for a remote pilot? That can vary between the type of equipment they're using and where they're operating. For example, are we operating at 400 feet and below in these small drones and they're not operating in controlled airspace, they're not talking to air traffic? Or are they going to be operating up in the NAS and they're going to have to talk to air traffic and deal with vectors and all that other fun stuff? So they're the ones working on that, along with 730. 730 is more of our scientists, engineers, and they're the ones also looking at the technology and saying what needs to be changed, what we need to look at, how can this work? And so a lot of them are actually working with many of y'all. I know that especially the NASA folks have been working with some of our people in 730. Katie Constance, who used to be here, she was going to be here today. She ended up leaving the FAA, great person, but she was one that worked with all these branches. 740 is air transportation. That's the branch I'm in, 740. We specialize in anything that's going to carry packages or cargo. Once you start carrying packages or cargo for compensation or hire, you now are considered an air carrier by DOT standards. And before everyone says, well, can that be changed? No, because it goes right back to the federal actual orders. It goes back to Congress. Congress got to change things. They did change a few things, but not a whole lot. They do still believe that we need to hold them to a higher standard than you do with, say, a private operation or a public operation. 750 is the ag operators, the public operations. You know, we got government entities that want to use them for surveillance or drop defibrillators off. They're the ones working those. You've heard of the swarms where they're doing these big light displays. That's all 750. That's all the commercial operations. And then 760 is the newest one. Just got stood up this year. If I'm speaking too fast or not loud enough, please let me know, because I am a fast speaker. 760, on the other hand, is an actual, we call it safety assurance office. So if you were to go to a FSDO, a Flight Standards District office, like all these ones in every major city around the nation, we have inspectors out there that take and handle the operators. They're the ones that work directly with them, certifying them. We started our own office for that because we don't have training for the field officers yet. So until we write the guidance, and like my division's got to write all the guidance, policies, procedures, and regulations. And I know everyone wants to ask about 108, and I'm going to help you out real quick right now. 108 we can't speak about, but yes, I am the writer for 108 along with many others. So I know what forwards and backwards. But the fact is we can't speak on those things, but we're writing the policy, we're writing the guidance. And that's what we do. Where did you put my clothes? I don't know. Where'd you put them? So 760 is our local office because we then work directly with them, and so it's a lot easier to get things approved and move faster through with them. Wing is finding that out a little quicker right now. We're moving fairly quickly on that. Okay, so what we've accomplished just in 1 year, and this is actually a very short list of all the things that this division has accomplished. We went through with streamlining our old Part 135. We have made it far simpler. I'm sure Mark could sit here and talk about how I've been working with Wing Aviation from the very beginning when they first started 8 years ago on working on the 135. And it took us a long time to get to where they're at this point. Now we have newer operators because we learned. That's the problem. You're new and you're the first, then you're going to kind of do the hard way until we figure out what works and what doesn't work. And so we've actually streamlined. So the newer operators coming up, Drone Up is out there, Drone Express is out there, and many others that you've heard about are out there working on these things and moving quickly through it. Response requests for UAS related supports, we're up to over 1,000 ag operators right now that are using UAS. It is now growing. They're averaging 10 to 20 ag operations starting up a week right now. That's how fast they're coming. And then also UTM, there's 2 operators certified right now to use UAS traffic management system, UTM, and Wing and Zipline, 2 people here. Y'all are the only 2 right now that are certified to be leads on that. There's others that are coming, and of course evaluating new operations. We also support, recently we've had several different operators come to us wanting to support some of the emergency operations going on out in the Carolinas, Georgia, and Florida. And so we were able to turn that over. We got the request for 1 operator, literally within 24 hours, we had them out there flying. That's how fast we were able to turn things over. Not letting them do that, but that quickly. We want to help, but we sometimes need time to get through it. Any questions? That is my fast brief to get through that.
I have a quick question. On the UTM approvals, are they only for company vehicles, or are they setting up UTMs for other people in that area?
Perfect. That is a perfect question. Mark, do you want to speak on that? I can cover it. So what it is UTM is UAS traffic management system. Wing was one of those that got certified. And what it is, and Zipline's the other one, it's not like it's hidden out there, the information's out there. So anyone that wants to fly in an area, for example, North Texas right now, there's one of the UTM sites set up. So anyone that wants to fly out there, since Wing is already operating that area, they can fly in the UTM. UTM keeps aircraft from using the exact same airspace at the same time. So Wing says, hey, we got an order in, and we're going to fly point A to point B, so we're going to block this airspace off so no one else can touch it during that short time that they need it. But now they have other part 130, not part 135, part 107s that are participating in that. Because there are part 107s that want to go beyond line of sight. Up till now, to go beyond line of sight was very, very restricted. We're starting to open the door a little bit because how do you avoid another UAS aircraft if there's not a UTM? And that's what we're looking at, is how we're allowing this to happen. So the systems actually talk to one another. So if, say, a public use operator wants to use Wing's UTM because they want to fly in that same airspace, then they say, hey, we need to use this airspace, and they can either give a circle, or they can give a line, whatever they need to do. They send it to the UTM. The UTM looks at it and says, okay, I can block that time frame that you need. Which now Wing can't launch any aircraft in that while that aircraft is in that frame. However, it goes a lot, and this is the really brush stroke one, and I want to say brush because it's a lot more detailed than that. It can actually track how long an aircraft's supposed to use it, and they can approximate where it is and as it starts to open up airspace, especially if one's going to go a long distance. This is strategic planning only. The UTM is only strategic. As everyone here knows, under the ASTM, strategic is just one step. That's your pre-flight. That's before you launch to prevent access. But now the question comes to the dynamic. And dynamic has not been approved for any operator yet. And that is where the UTM's got to know where every aircraft is at all times. And as we get to dynamic, then they can launch them closer together and make sure they avoid one another. But what we're finding when it comes to that, different operators have different emergency procedures. Let's say that there's a DAA, detect and avoid system on board. Some will stop, some will slow down, some will vector into a different direction. Okay, but that all affects the UTM. So you've got to put that into the planning right now. In strategic, they go, so well, got to give an extra 30 seconds so they have time to do their DAA if it happens. As they get to dynamic, they might go shorten those time frames and get closer to them. Does that help a little bit?
Yeah. I was just wondering if they are trying to set it up so that other people can use it.
Yes, it's already open. I don't, and the question we've been raised is there going to be a cost to it? I don't know. We're not into that side of it.
Yeah, I mean, it raises all kinds of interesting priority.
Yeah, if I could speak.
Yeah.
Just real basically, yes. I mean, so it is, it's an implementation of the ASTM F3548 interoperability standards. We're basically taking that standard, putting it into play here. And so, yes, like Zipline and us talk to each other with our reservations. Anybody else that joins that, there's a whole governance structure for how this works. This is industry led, and then one of the big things we wanted was industry to show that we completed it. So there's a governance structure for that, and other companies can join that, participate in it. There's an onboarding process, but it's intended to be shared for each other. And we have, north of Texas, there are numerous operators want to fly in the same airspace. The problem we have to solve. It's a great place to try that out. As we learn more, the ASTM standard will be updated based on the feedback there. So it's an iterative loop. And one of the hot topics right now is about prioritization. How does the emergency responding vehicle get dealt with first? And so that is like the current work effort is prioritization.
Cool. And I should say the ASTM standard allowed room for prioritization, but it didn't set the policies for prioritization. So the governance documents need to set the policy.
Right.
The technical standard supports the prioritization, so that the foundation is already there.
And the regulator has a strong perspective on what prioritization policy should be.
Right.
They're involved in that session as well.
So how does BV loss, you mentioned BV loss, how does BV loss play into that? I didn't quite pick up.
So if you want to be able to go beyond visual line of sight, you have to have, and this is right in my part, 3 DAAs, detect and avoid. There's 3 things that you've got to be able to do to get into an airspace to go beyond line of sight. Number 1, everyone thinks of DAA, you think of detect and avoiding a manned aircraft or crewed aircraft. Okay, that's of course a high priority for us. All right, can't argue with that. So you avoid that one. Well, what about number 2? and that is the unmanned aircraft. And that's where the UTM comes in and now allows multiple UAS to fly in the same area beyond visual line of sight and still be able to avoid hitting one another. Because we don't want two UAS hitting each other, because even though there's nobody on board the aircraft, it's what's underneath the aircraft. Remember, when it comes to FAA, we're responsible for not just the sky, but also the ground of who that object can hit. And so that's the second BAA. And my third one that I have to tell people about is detect and avoid. It's just that. It's three little letters: detect and avoid. You've got a crewed aircraft, you've got an uncrewed aircraft, and you have a ground obstacle. And that's the biggest one that we find a lot of operators. What do you mean? So I got to see obstacles on the ground. Could be trees, could be hills, could be buildings, could be structures. And we've had operators hit ground structures beyond line of sight operations. I won't say which operators have done that, but we've had more than one hit that. And so we have to go back and ask that operators, like, how are you going to avoid that from happening again? Give an example when it comes to ground obstacles. Here in Dallas, there's a lot of construction going on everywhere, right? You know how fast they can pop up a sky crane? And it could be a couple hundred feet in the air in literally overnight, just about. And so that can be something that these operators have got to watch. So some are using a mapping where they're looking at the ground and determining where there might be operations or something going on. Some are using software that actually sends out signals. We have some that use sound. We have ones that use video cameras. We have ones that use LiDAR that are testing different processes to avoid these different things. Does that help?
It does. Does BVLOS need to interact with the UTM?
Yes. Well, that's just it. The UTM is actually one of the steps to help. Is just one of those three DAAs. The UTM is the DAA for the UAS from hitting another UAS.
Number two, right? But then you have to have one and three also.
Yeah, so it's just one of
That's the strategic one, and then you need like a tactical.
Well, yeah, see, then you gotta look at how are you gonna detect and avoid unmanned aircraft. Some are using microphones and LiDAR and all kinds of things for that as well.
And then you're gonna have approved algorithms.
Yep.
Right.
Yep. It gets deep. Yes, sir.
Just a follow-up. Is the assumption right now multiple operators, only one UTM service provider, or are you considering multiple UTM providers?
Oh, no, they're gonna be as many multiple UTM providers as they want. Right now, only two of them have gone through the process of getting their certified, Wing and Zipline. And Wing and Zipline can fly in the same airspace, or they may be flying in totally different airspaces, but they still talk with one another. That was the interesting thing I found is that even though Wing's flying in Dallas here and Zipline's flying in another place, they're still talking. They're going, well, I'm not flying there, so I don't need to worry about that one. But they'll check with all the other unmanned operators that decide to use their UTM. So some may contract with Zipline, some may contract with Wing to use their UTM so they can avoid one.
Yes, segregated. So Zipline UTM, Wing UTM, do not overlap.
They could overlap. They could both be in the same airspace.
And
But they have to be talking.
include the DSS.
Yeah.
Who runs the DSS?
So the DSS is an instantiation by both companies. There's an interface between.
So it's a distributed DSS?
Yes, I think so.
And they talk to one another the whole time.
Yeah. That's my understanding of it, but I'm not UTM guy exactly, so I'll defer that.
So I should ask someone who knows?
You should ask someone who knows. Yes.
Well, it's all new, not real clear.
Yeah, that's right.
I mean, there's a lot of detail behind it, and there's a lot of structure behind it. I just am not that personally involved in the programming of that. So
I'm not an engineer. I'm a pilot by background. So I specialize in operations side. And when it gets to UTM, you're talking about an engineer that can dig into the software and understand it. And I looked at it when we were talking about, do we need to validate this thing when it came to UTM? And so I raised the question. I was talking to Wayne and some of the others. So how do we validate this? What are we going to see? If I have two operators flying the same airspace, what am I physically going to see? Well, you're going to see one aircraft not launch. But that's it. You'll never see anything like any. So we're like, this is where the engineers have got to be able to look at it and tell us, yes, we're good with this. It meets the standard. Okay, then I put my hands up and say, okay, it's all yours. Yes, sir.
So I'm at NASA and I've seen early iterations of UTM, but I don't know how it's morphed over the last 5, 6 years. So is that something we could ask for in the future and working group is like an engineering explanation of how you.
Oh, most definitely. And we have done that even from my side in the FAA. And I've had to go to, remember those other divisions? I've had to go over to those other divisions where the engineers and scientists all sit and go, can someone explain this to me? And even they sat there and scratched their head, well, I think I understand what they're saying here, but here's what we understand, and they have to talk to the operator. So it's one of that even I got with Wing, and I got with all those engineers, and the engineers like, give it the water rhythm.
That's what it worries.
It's custom and,
Yeah. But I think you're right. I think if we can identify the folks that make sense to invite from the FAA and from NASA and industry, maybe we could have a session that focuses on.
How much of that are we gonna see tomorrow?
We're not gonna demo UTM specifically. I mean, it's not to our operator, to our pilots, it's relatively transparent,
The pilots can't see it. There's nothing they can see.
Right.
Yeah, I think like researchers, like this group especially needs a technical understanding of how UTM is
Probably
has evolved over the years.
Peter Sachs or somebody should.
Yeah, Ronaldo or someone. I mean, it'd be interesting to like describe, especially if it's the governance structure and the checkout process, like, so the actual ability to put this in place and use it for deconfliction as a safety, and get credit for safety requires the technical checkout of that, which that checkout process was approved by the FAA, at least the testing that goes into it. So you can't just say, oh, I have UTM and I'm good now. You have to meet some bars, and there's a number of companies that are going through that process right now. We expect to have a lot more than just 2 in the near future. So a deep dive would be helpful, I think, especially if the way the structure works. I mean, the bottom line is we are actively demonstrating that you can fly numerous aircraft at the same time in the same airspace and never hit one another. But we should walk through it.
When I talked to Peter about having Zipline speak, we talked about that or an end-to-end discussion. And I think tomorrow's presentation is going to be more on the end-to-end, not on the UTM airspace side of things. But, I think, if the timing wasn't the way it was, we could have gotten Peter to this meeting. He was intrigued. So.
We could have started with ASTM last week down here too. Maybe not.
Yeah. Okay. You have a question? Yes, sir.
Who manages the DSS now and in the future? So there's a word that DSS is currently distributed, but I think in the end, there will be one person who manages DSS. Can you answer?
I didn't hear the very first question.
Who manages the DSS?
Now and
So I think the way that my understanding of F-3548 and the way the DSS is designed to work is still being federated. Still, that synchronization service is accessible and hosted by multiple different people. Still talking to each other, but I am not. That's that DSS side. I am not the person to talk to in detail. But I know from our perspective, we would like to see multiple. It not just be one company that owns one company or one user that owns that thing, but find a way technically to allow multiple people to, as long as we can ensure safety and quality.
Someone can't just automatically start a DSS and say, I'm going to start using this. Anybody that has a DSS has to go through a certification process. And they do go through the FAA, and we have our own engineers and software specialists and all look at it, and they do their magic behind the scenes. I'm sorry, guys, that's not my subject. They do their magic behind the scenes, and they come out and they say, yes, this looks good. So then it comes to me, and I go, okay, so I can then add this to their authorization. And that's what I do, is I gave it to Wayne through their op specs, and to a non-air carrier, we give them an LOA, letter of authorization, say, okay, this system is usable. But it's got to be able to show that it can communicate with the multiples of the operation. It's not as simple as just creating one and then training loose.
Other questions?
Just real quick. We're a little bit short on time now, so I think we should.
We've got like a dead hour at the end of the day. I think this is a good discussion. People have questions. Thank you, Doc. Appreciate you. Someone paying attention.
And so I can wear it a watch.
He's starting to get into his retirement plan early. So I'm gonna make it easy for everyone. My first name is Timothy. My last name is Beglau, B-E-G-L-A-U. It's timothy.beglau@faa.gov. So if you want to send me an email and learn anything more, you can send me an email. You're more than welcome to. I think I actually had it up on the first slide. Please do, and even if I can't answer, I do route it to the people that do specialize in that, because there's a lot of questions that I don't answer, and I send it over to them. It's interesting working as the team, as you saw earlier. We work as a group, so this is where I sit, but I'm constantly talking to every one of these groups all the time. And I'm in meetings almost every day, multiple times a day, to talk about C2, UTM, this operator, that operator. And we're constantly figuring out what works and what doesn't work. So it's a big process.
Thanks, Tim.
Thank you.
One thing I'll just mention as we change speakers here is that part of the reason we put this group together was that if you have ideas that you want to test out, if you're starting, to think about how the development of UTM or DAA algorithms or DAA displays or anything like that, it's nice to have the FAA take a look at that early on. This is a venue where you can bring some of those ideas, discuss them, talk to people who've been working in these areas for a while, get some feedback, and so that it's you're not, the first time the FAA sees it isn't, when you're applying for waivers. Okay, we're moving on to Mike Litowitz, who's going to talk about what are we doing with these white papers.
All right, this will be very quick, really a short answer. Basically, we looked into a couple different options for publication of the white papers. Ultimately, we needed to find an avenue that worked from a NASA perspective, also gets some reach and be publicly available. So we're going to publish them as NASA technical memorandums, so NASA TM. Those will be available on the NTRS server, so again, publicly available. But that allows us to, basically on the cover page, it'll have a compiled by name. So someone will be designated as the compiler of the document. And then on a subsequent page, it will list all the contributors and their affiliations. So we're able to include everyone and their affiliations without them having to have some contract with NASA. And that was kind of our goal here, make sure we can include everyone's names and affiliations as we publish these. There's no mandatory format for this. I think we have a format for the cover pages, but other than that, as long as it's consistent for the document, we don't have to keep any specific format. And yeah, I think that's pretty much it. We've got our templates. We'll get that to the title pages. We'll get that to the leads of the working group, the breakout groups.
Is there a specific review process that these go through?
Yes. So with this, they'll go through a system that we have called Strives, and that will go through several layers of review. And a lot of that is, it shouldn't be any sort of issue. It's more just it'll take some time to get through that, depending on who submits it.
Yeah, we may strategically submit it.
Yeah.
But the other thing is there is a requirement for 2 peer reviewers, internal to NASA.
Yes.
So this these papers will require 2 NASA peer reviewers who are not named anywhere. But for to be quite frank, before it even enters the release process, it has to have those peer reviews.
Makes sense.
And so we might want to think about who those peer reviewers might be for these 2 papers, or 2 or 3 papers, depending on how many we end up doing.
Yeah.
I think those are typically NASA people, but I think they can be external.
They would have to be, there is a mechanism for external, but it would have to, they'd have to have an agreement.
Okay.
For that, but there are mechanisms to do it external.
Sounds good.
Yes, and Mike, are there other do's and don'ts, such as like inclusion of photos and how you
Good point. Yes, so with photos, and I think you've probably been through this process with your slides now, a few times. Yeah, any photo that's included, any graphic, it needs to be in the public domain or have permission from the person who created the graphic. The legal department will flag those and ask us to get permissions or remove them. So yes, good point. Thank you for bringing that up. Yeah, that's one big consideration with the publications.
Yeah, and not just photos, but like a diagram. There's a diagram that is used to make a point. It's better to draw the diagram.
But yeah, other than that, I think it'll be, like I said, on the NASA server. If we want to advertise these somehow, we can point people to the document there. But there's no inherent conference associated with this or anything. Those other considerations that we would do this through like an AIAA publication or something. So that's something we should probably talk about too, is how do we want to get this out to people and advertise that it's available once we do publish it, because that's not built into the product. But we do have a way to publish, so that's good.
Yay. All right, thanks. Okay, we're going to start going through the white papers now and have a little bit of discussion on what's in them. Jonathan, do we have Merhans on online? We do. Okay, she's going to present second, I think. So okay. All right. So let's go to my slides. So just to go back to that for a second. So instead of me sort of babbling up here for an hour, I'm going to just talk very briefly for a few minutes, and then we're going to get people up who are actually working on particular things that you haven't already heard about. So, okay, next slide. One more. Let's get there. Okay, so this is our outline. It's not formatted very well for presentation, but as you can see, we've got some background stuff up in chapter 1 that I think still needs to be actually worked on, the intro stuff. But then we get into the strategic commands that Mark has talked about previously. Here it's listed as aircraft versus area commands, but that'll be an area in there. We have a strong section on safety case, which is down somewhere below. Oh, it's up there. Yeah. Oh yeah, safety case 4. We have a number of sections on specific metrics, situational awareness, workload, those kinds of things. And then the metrics that you guys have all heard me talk about, the neglect time, which is now intervention time, coupled with service time. And I've written a section on that. That'll be part of this. So we won't go back through Mark's strategic commands and my intervention time stuff. We will move on to some of these things on the safety case, the modeling and complexities, and some of those things to give you a little bit better feel for some of the other stuff that's in the paper. Okay, can you just go to the next slide? That's all right. So I think we're maybe 75% done. I'd like to say 90, but I think we're probably closer to 75. There's a lot of details, summary sections that have to be written, transitions between sections where we have one author, different authors writing stuff that it doesn't flow very well. I think we're pretty solid on our intervention time, service time, workload, strategic commands, system team performance, safety case, and complexity. These are all sections that I think are fairly complete, pending some reviews. We do have a lot left to do, though. Well, 25% maybe. Next slide. As I was saying, sort of the flow, try to make it sound more like, you've all read these papers that clearly have one author that wrote this section and another author that wrote another one. And it's better if you can get the flow going. We have to do some transitions and consistency. We probably, this is something that Andy's hit us with a few times, that we use some terms pretty loosely at times. We need to make sure that at least within each of the white papers, we're at least internally consistent with that, if not consistent throughout all 3 white papers. A couple of big things we have to do work. Integration of the interventions paper. All along, Andy Thurling, who couldn't be here this week, he's got a flight test going on, has been leading the group on interventions. Garrett's going to present for that. The idea has kind of been that we're going to integrate that into this white paper because it makes sense to be talking about the intervention time and service time and then discuss intervention. I don't have a real feel for how that's going to go. That could be a bear, and it might make sense to leave it separate. That's some of the things we have to discuss, I think, at this meeting. And then they reworked. Remember, I put together a little scenario, a little snippet, so that I could exercise the intervention time and service time examples. They have reworked that pretty significantly. And the original idea was that we would all use the same sort of example so that a reader could read through and recognize that example. And now they're doing it with the exceptions, and now they're doing it with the metrics. And so we have to work through that and make sure that it's still consistent and makes sense, and we have to do that. I'd like to get these things done and the summary and the next steps in the next month or so, and I think that that's a reasonable goal. This is my last meeting, but I'm still gonna work this over the course of the next month or so to try to get it to a place that we can get it to those internal reviews, and that's about where I'll hand things off. Okay, I think that's all I had. Is that true? Let's see. We'll go to the next slide and see if there's anything.
That's it for yourself.
Okay, so we're going to try to do a remote presentation from Murnaz Sabat, who is getting her PhD at Cornell in human drone systems, which I didn't know you could do that. But that's the idea. So we'll see if Jonathan can make this work. But she'll be talking about the safety case. She led a lot of the effort on the safety case, which is critical, obviously, to anyone who's trying to get FAA certification.
Ernest, are you online with us?
Hey, Jonathan. Yeah, I am. I just need to get the permission denied issue resolved in a second.
Okay.
Hey, everyone. I'm going to be presenting our chapter for data for safety cases. Our subgroup includes myself, Radhika, and also Katie from the FAA. So starting with the motivation for this chapter, we probably all know that the traditional safety assurance methods do not work for the MN operational scenarios that we are trying to look at. So we kind of argue that a new framework is needed in order to guide the comprehensive data-driven safety cases that are required in the MN operational scenarios. Kind of to talk a bit into our approach that we've taken for writing this chapter, we try to come up with the core components that a safety case framework should have. And these components are not new. In fact, we have taken inspiration and looked at references into the traditional data for safety cases framework and what are the core components they always look at. So we try to kind of adopt those core components, bring them here, and instead then under each core component, write how they should be utilized and adopted for MN operational needs and scenarios, and what are the specific challenges that are different compared to the traditional methods. So that's our approach. In terms of the core components that I just talked about, we look at 4 main components. So first and foremost is mission. We look at the mission safety. Then after the mission and the components that people need to look at the mission level, we look at aircraft safety and what are the types of aircraft I'll go into more details for each of these core components later on. So mission and aircraft first, and then we talk about the human factors that goes into the operational side of things, and, the supervisory roles that the operators need to take. And then we talk about the environmental hazard analysis and what are the things that people need to look at there. So this is how we've divided up the core components, and kind of to put it into perspective of the pattern that I just talked about. If you follow from the right side, for example, I talked about the core component of mission safety. Under mission safety, we go into details of thinking about the mission type. For example, is it a passenger delivery kind of a mission? Is it a cargo delivery? And based on a mission type, we talk about what is the difference in terms of the data to look at. And then we talk about mission configuration. We first talk about it at a high level, and then we talk about how to apply it in the MN operational scenario. For example, if mission configuration needs to include all the parameters for the mission, like flight plans, we talk about the fact that in an MN operational scenario, some parameters matter most, like, for example, collision avoidance between the UAS and the missions that have interdependencies between each other. Then we go into the aircraft safety. Similarly, we have like subsections for that. We go into the aircraft type that is considered for that mission. And under aircraft, we also talk about not only the system itself, but the subsystems that people need to look at, like the navigation, communication, detect and avoid on board the aircraft. But then again, following the similar pattern, we go into like details of how that changes when you're looking at it at an operational scenario. Then we talk about performance indicators similarly, and we talk about safety fragments for aircrafts. That includes like what are the fail-safe mechanisms that have been implemented at an aircraft for the aircraft's mission and the subsystems. Then on the left side are the two other components. I talked about human factors. Then again, following the similar pattern, we talk about like workload training that the operators have received, the decision making, but then going into the detail of when we think about it in an MN operational scenario, things changes. For example, have the crew or the operators taken any training in terms of controlling multiple aircraft instead of just one, and how does that change in terms of the data that we need to look at? And finally, the environmental hazards. Again, we talk about, for example, weather patterns, terrain features, where the operation is taking place. These are kind of, even for a single aircraft, parameters that we need to always look at, but then we also talk about how to apply it in the MN operational scenario, to talk about the weather patterns that, for example, can affect multiple drones, and how should those risks be look at when they have a compound effect. So this is the overall framework pattern that we've taken. To kind of show you how these subsections look like at a high level, here is, for example, one of the subsections under aircraft safety, which is the performance indicators. As you can see, we start talking about general parameters that you need to look at for performance indicators when you're collecting data. For example, system reliability, maintenance records, operational performance matrices, and all those essential parameters. But then we dive into how MN changes that or requires more data to be looked at. For example, we need to extend the parameters beyond what it is for a single aircraft to measure system-wide reliability. Communication becomes very important, so we need to look at coordination efficiency, and the performance indicators need to cover, for example, how a UAS fleet might maintain cohesion, avoid conflicts, and respond to the dynamic changes in the environment. So this is kind of briefly how the subsection contents look like when we try to look at it individually and also in the context of MN operations. Now I'll pass it to Radhika to talk about kind of sorry, before I pass it to Radhika, there is this section after we talk about the core components. We kind of reflect on this higher level section of how to collect data and perform data augmentation for all of these core components that we have in our framework. So data collection and augmentation at a very high level includes how to use, for example, sensor fusion, how to use simulations, and how to do real-world or real-time data monitoring and collection, how those data can come together, and which parts require more data, and where we have limited data and we require more data augmentations. There in the section, we talk about machine learning approaches and data integration approaches, for example, combining synthetic data with real-world data to kind of collect and reflect on the data patterns that we require for each of those core components. Again, just as an example, for example, this is the section, the subsection we have on the simulations. We first talk about, on a high level, advantages and limitations of using synthetic data on simulations. For example, you have access to a risk-free environment. You can do scenario testing very easily, which can be a powerful tool. But we talk about the limitations of like sync to real gap and the real-world variables that are quite different than the simulation, and the simulation does not capture that. The cost of the high-fidelity simulations that are required, but we also reflect on the challenges that are specific to DM and operation scenarios. For example, we talk about the fact that simulations need to model the interactions between multiple UAS, and they need to capture the complexities of the communication and coordination between all these different UAS that are involved in a mission or multiple missions simultaneously. These subsections also follow a similar pattern. Now I will pass it to Radhika to kind of talk about the human factors in our chapter and kind of reflect on how the core components connect to these data collection methods that we have when they all come together under a single subcomponent.
Gathered is the competency and experience, the workload, situation awareness, trust in automation, and also trust in the team members that they're working with. So many of these come from my experience with from the project which I worked on with Anson and Matt last year, wherein we conducted like flight test operations. So on a team level, this is not an exhaustive list, but these are like the starting points of variables that we may need to consider when we think of gathering data. So the collecting data for time required for human-human and human-machine communication when there are multiple disruptions occurring. So for end-to-end, there will be like multiple disruptions on multiple vehicles occurring at the same time. So how does that affect the time that is required to communicate? Then the phraseology that is utilized while communicating. Why this is important is because that will kind of govern the length of time that goes into communication. Then rate of overlapping communication, especially in off-nominal scenarios, because when there are multiple number of vehicles and correspondingly an increased number of people working with them or managing them, there are high chances that the communications get overlapped, and which kind of increases or it surpasses the available window of reacting to a certain off-nominal situation. And then frequency of gesture and verbal cues. So when we were conducting flight test operations, it was like the remote operator and the supervisor were located in the same space. So they had the flexibility to give like verbal cues and gestures to like inform each other and gain a shared understanding of the situation. So how does that like progress when there are more number of disruptions occurring? That is another variable that we can consider. So to collect this data, there are different methods that we can utilize, which is flight logs, then interviews, focus groups, and they may not be after every operation, but like on a periodic basis. Subjective ratings, eye tracking, like all the physiological data measurements, and then ethnographic studies during the simulation and real world data collection. But yeah, I'll pass on to Meher and ask for touching upon the other parts of this framework.
Great, thanks. Do you hear me? Just to make sure.
Yeah.
Okay. So kind of continuing on that, we close our chapter with a final section called complexities, where we reflect on the complexities of collecting all these data for all these core components that we mentioned. On the complexities, we've divided up the complexities to data-driven risk assessment, safety assurance in autonomous systems, quality and quantity of the data, and automation layers in MN. All of these sections have details on what makes them complex, but to kind of briefly go over two of them, we've included data-driven assessment here, for example, to show that we reflect on the fact that a data-driven risk assessment requires collecting diverse and larger scale data that cover this distribution of exceptions that can happen. But when we talk about the MN risk assessment, we need to go beyond a single point of failures. So these risks can stem from interactions between multiple vehicles or interdependencies between the missions. It can come from components like system of systems components or kind of human machine side of things. And the assessment and the data and the risk assessment needs to kind of completely cover all these scenarios, which makes it far more complex than a single vehicle kind of a risk assessment. And also another part of these complexities that we've reflected on goes into the automation layers in an MN operation scenarios. So here we reflect on the assignment of roles between automation and human operators. We talk about how hard it is to assign these roles specifically, but we go into an example of, for example, if there is an automation assignment, perhaps tasks such as path planning, collision avoidance, or real-time coordination can be completely kind of offboarded to the automation. But the challenge of that is that the data needs to kind of demonstrate that those automated systems can actually reliably handle all these automated systems and that are required. And we kind of go into the complexities of covering that. And again, on the other side, like if operators have specific roles, the intervention patterns are quite challenging, and the data collection should kind of cover the intervention rates that are required for the human operator and what happens when the situations are quite high stressful or the interdependencies between the missions are a lot. So this is also these types of sections are how we cover the complexities and kind of conclude the chapter. With that, I'm going to ask for questions or any feedback from the audience if we have time.
Marnez, this is Jay. I have one question. Is there any guidance, or have you guys looked at how you can combine? You've talked about several different sources of potential risk, and they're not independent, right? And so how can you combine and try to account for the interdependencies between the different risk drivers?
That was one of. So Venus, do you want to take that?
Yeah, sure. So in fact, when we kind of separated the components, one of our goals was that it will be easier to look at each component and risks under each component and then come up with a way to connect them together. For example, in the chapter, we talk about risks of just aircraft safety and fail-safe mechanisms of the aircraft within an MN operation scenarios. But then when we go to the mission, it becomes not just about the aircraft, but at a mission level risk analysis and the interdependencies between the mission. So because we did the component kind of level first, we thought that following similar frameworks that we saw in the references, it will be easier to connect them. But another challenge about it is that a lot of these things that come up about the interfaces or interdependencies in an MN operational scenarios, there aren't many actual insights into how to collect the data for those risk assessments. So we kind of had to take in like a lot of creativity in terms of coming in with suggestions on how to do it. But that was actually one of the things that we needed feedback on, how it would be easier to connect them together to give a comprehensive kind of risk assessment tool as part of the chapter.
Thanks. Comments?
I have a question for Radhika. You mentioned collecting data about trust. I'm wondering if you could talk about, like, is there a framework or a model, or how do you standardize your measurement of trust and perhaps over trust on
So the one way that I have come across in papers, like the papers that I've read, is having subjective ratings about different things. So it's a survey, and then there are a list of questions that are tailored to the context of operation. So usually these scales are like generalized scales, and then you take those questions and tailor it to your operation and then give it to them.
So it's all self-reported.
Yes.
We've been, some of us have some issues with some of the trust literature. And
you don't trust the trust literature?
And I feel like it's sort of an intervening variable, because in some ways we don't care about trust, we care about whether or not they use the system, right? So it's more of a utilization score, and that's a performance-based score that can be an objective measure. And I think that might be a cleaner way to try to get at whether or not someone trusts the system.
Yeah, but a good point was raised about overtrust.
Yeah.
And so utilization,
they
can over rely on a system that is not trustworthy, and doesn't deserve the trust of the user in the way that.
No, we want calibrated trust.
Calibrated
Right.
trust, amen.
Yeah.
So the subjective, do you trust it or not, is not sufficient, whether they are matching the trust with what the system, is capable of doing. Basically you want calibrated trust is basically the amount of trust matches the competency of the system. And how do you measure that? Have you looked at that at all?
And along with the understanding of the system, like system will behave, or the boundaries of the system. So along this, and I think you just talked on a very important point wherein a yes or no is not enough. And that's where interviews and focus groups come into picture, when you probe the participant or the crew members who are performing an operation to kind of get out of them how much do they know about the system, and based on that, how much do they trust the system.
Anybody else?
Question about
Yeah.
risk priority number. Is that such a, I know it's a risk, but I didn't see any of that. Is that not useful here, or? You could boil it down to numbers that are made up of multipliers and addition.
You mean like a risk by likelihood sort of matrix?
You can present it a number of ways, but it's a numerical estimate. You'll never get it right beyond the first decimal place, but that's okay. You can see how it flows, how the different risks flow into your final answer.
Yeah, you can take this, but it seems to me what they've done is try to identify the potential hazards and risks that you would want to take that next step with to develop that kind of numerical scale.
Yeah, that's right. And like, we think that it's not supported to have like a quantitative measure, but like supported with qualitative analysis, because, for example, trust, it is a very subjective variable. So even if we generalize it with like quantitative like numbers, it's not going to do justice to what that case is actually. So the more qualitative data that we have on it, it makes it richer to understand how people deal with these systems and how we can improve the system.
But I think your point is good. The circumstances that you're in are going to have an impact on what the consequences are of the system's correct behavior or incorrect behavior. And I think having that, you have to have the trust tied to the operating conditions under which the system is being used. So.
Yeah, and then I think if you follow along with that, then you have mediations for those high-risk conditions.
You can identify where to
Yeah,
intervene, right?
exactly.
What's the real problem?
Oh, that's his real,
Right,
this is
so
a high one.
it's not getting the number right, it's really identifying
Yep.
sensitivities and seeing where the bottlenecks are.
And when you're at the boundary of that performance.
That's right, and when it's totally unrealistic, that's right, yeah, like, oh, don't do that. Right, don't do that.
Okay, thank you very much, appreciate it. Disney, we're almost on time. We're almost on time. So like 15, 20 minutes?
Sure.
Disney is at NASA Ames, PhD from MIT, right? And works in the TI division. AF. I should have got a bio. But anyway, Susan is going to talk to us some about some work you've been doing on modeling and data analysis.
So like I said, I'm going to cover two areas that was under the outline that Jay showed. Some aspects of complexity that I provided, and then on the modeling. And I want to emphasize here what I mean by modeling, or the way I talk about modeling is more fitting models to data rather than simulation. Right. So on the complexities, like I said, I did this other activities I did on autonomy metrics and measures, and so I kind of generating my white paper on may go beyond end-to-end. So I have a framework that's more generic, and I'm trying to see how this actually fits you can use here as well. So there's going to be potentially overlap between some of these notions and what Radhika, what's the name of the other? How do you say it? Meta-analysis. It just presented. So I actually also sort of looked at how do I approach complexity for this? So there's a performance of the system, which could be safety, efficiency. So if you think about that's going to the system to be safe, how does complexity affect it? So I think of complexity as factors that ultimately affect the safety, efficiency, and performance of the system. And I kind of divided or proposed in this paper to divide complexity into three elements or three dimensions. The complexity of the task that need to be performed, and the complexity of the agency that is performing the task. In this case, it's rather complex, but it's end-to-end, vehicle air traffic control, and UTM, and all these things. So lots of complexities on the agency side, who's performing the task, and then the environment, where and when you're performing the task. Weather, lots of traffic, lots of uncertainty in the environment that affects the complexity. And so in the white paper, I provided a few pages where I take each one of these, the task complexity, the agency complexity, and the environment complexity, and provide some few points on that. So that's kind of at a high level what that contribution is. And I'm going to take a couple of them here on the agency side and the task side, and drilling into them. So there's no time to go through all that drilling here, but just to give you an idea. On the agency complexity, we have the basically the remote pilot and the vehicle on one axis, and then we have the automation, remote pilot versus ground station automation. So if you have to take some function like separation, you can have what are the roles and responsibilities? Where do we put that function? How do you distribute and allocate that function across the pilot and between the ground and the air, for essentially the pilot and the ground station and the vehicle, but then on the ground, the human pilot versus the automation. And these are the two dimensions. And there are lots of scales there in the literature. This is just showing a few of the scales to go from completely manual to completely automated. So Radhika mentioned the layers of automation. So there's overlap here between these, and we see. But there's an interdependency here that Jay mentioned, because when we're talking about end-to-end operations, we can have the choice to have the automation in the ground station and uplink the decisions from that to the airplane. But we also have to think what goes on the vehicle versus what goes on the ground at the ground station. And particularly if you lose link, you really don't have access to the vehicle. Things have to be on the vehicle. So, but if things are on the vehicle, that enables end-to-end as well. So how do we decide overall what goes on the ground, on the ground station versus the vehicle, and then what the remote pilot does as a human versus the automation? And these are just questions. There are lots of complexities there. Some of these were mentioned already. We need metrics to see what very clear lines of responsibility between the different agents in the system and the dynamic nature of it. We've done some research here and the transition. If you have multiple pilots, multiple vehicles, how do you transition between one pilot to another? How do you shed some vehicles if something goes wrong? And so we need lots of metrics to deal with the complexities in the dynamic environment and how you transition. And there are dependencies on the timescale, for example. This whole picture might change if you have the, collision avoidance where you don't have time to react versus strategic, like we're talking about some responses might go to UTM if you're very strategic. So these are complexities, so some additions to what was mentioned already. On the task complexity side, again, there are a few areas I want to mention. One of them is discretion. A lot of times the task that you need to perform in aviation is not really defined as a series of activities, it's defined as a goal. The pilot is responsible ultimately for the safety of the flight. Air traffic managers maintain safe, orderly, expeditious operations. So how do we trust the human and how they ultimately can decide what to do to maintain the safety, for example. But when we do automation, we do lots of automation to support end-to-end. What do we do that discretion that we usually give the pilots? How much would a pilot who's controlling multiple vehicles at the same time, how much discretion do they have versus the pilot who's handling one vehicle? With a lot of automation, that's going to be reduced. And do we give the automation as much discretion as we give the human pilot, for example? On the structured learning side, I also added a few comments with what I provided on the effect of learning and what Trust was mentioned, for example. So on the human side, we build the skill into expertise and we grow to trust the human when they become experts in flying, performing surgeries, etc. And now that we are having one pilot remote, with multiple vehicles, how do we achieve that learning? Air traffic controllers, there's an analogy, and I come from air traffic control side. Air traffic controllers do a lot of things to reduce the complexity of their task by grouping vehicles, grouping instructions, and creating basically patterns that structure the task more. Are there going to be things similar on the M10 now with one pilot to many vehicles? The vehicles are in different parts of the airspace, so the whole patterns can be different. But we may see a learning curve for the pilot handling multiple vehicles where some new patterns may emerge that the pilots use to structure the tasks more and make it more possible, kind of following what air traffic controllers do over the years, but in really different contexts, different tasks. So I talked a little bit about that. And then the uncertainty not only in the environment, but the task itself. Like I said, sometimes the task has also discretion, so there's uncertainty in the task itself, and also uncertainty in the environment. And the remote pilot deals with those unknowns. That scapegoats all the way to the high levels of uncertainty. And how would a human pilot that's handling multiple vehicles deal with those high levels of uncertainty compared to one-to-one? So anyways, maybe a few added points to what Radhika and Mahna mentioned, and we'll see whether this will be a separate chapter or this will add to the complexity list that you mentioned. I don't know whether the approach is going to be, this white paper could be a collection of papers, and there could be overlap or even disagreement between them. That would be one approach. Or we can look to integrate these things more, so we can talk about that. But there are a few added points that are provided here. And there's references to some papers that I also did on these different areas. I'm going to move to the modeling side. Okay, so I'm fine. So maybe 5 or 6 minutes on this or 10 minutes. Okay, so we can think of this is going to be more along the line of modeling on the task complexity side. I mentioned a few words in the write-up on maybe we need metrics and we need modeling on the agency side. Maybe networks of teams and topologies of network and such. I think there's lots of issues there. On the task complexity, I've been working on an effort to say, and I think this really jives with the whole theme of the paper here, with the interventions and the rate of interventions and such. And so if you have a remote pilot handling multiple vehicles, and the idea here, I know I do not say there's a more focus on the small drones which might be operating in a non-controlled environment. But this work, I spent some time working on the use case of the larger drones that may be actually talking to air traffic control at the same time, which I don't know. So for those who are small drone inclined, bear with me. I mean, the exercise or the example that I'm giving here is more for if these vehicles flew and it's just like an IFR aircraft and potentially controlled airspace. So let's say there are 3 sectors and the remote pilot is supervising multiple aircraft in multiple sectors. There are issues there in terms of listening to multiple controllers at the same time. Even if you're on controlled airspace, you're on the CTAP, common frequency, and you might be listening to multiple chat channels, with other pilots as well. So there are these types of issues, and you might be getting instructions at the same time from multiple controllers. So how do we handle these things? So this is kind of a task that's very complex, depending on the environment. And how do we model essentially the workload or the task load, if you will, of the remote pilot when they're bombarded by these communications and interventions? And so we did some data analysis taking trajectories of aircraft, and we tried to use a model where we separate out basically small deviations that maybe just require attention, maybe bigger deviations with trajectories that require action, and there's maybe even bigger ones that require communication. This is, like I said, in the class of statistical modeling. Okay, so the idea here is if we take data that may come from historical track data, or maybe you conduct a simulation, you generate trajectories, you generate data. So you have trajectories. And the idea here can be statistical type modeling of analyzing those trajectories, fitting models to them, and identifying some of the parameters. So this is what we're talking about here. The parameters can include things like what are the distributions of these intervention times, what's the service time of the remote pilot servicing multiple at the same aircraft at the same time. So if they're on the high workload, what is their service rate and such. Can we infer these from data, whether the data is coming from historical, actual, real, traffic data, or from simulation data? Okay, so so the idea here, again, if we take that example of 3 different trajectories, 3 different sectors, if you have, from one sector, there's the entry time, and then there's changes in heading and altitude and speed. Now, if you're handling another aircraft at the same time on that timeline, you see that you have to handle more. So the time in between the events become less. If you have 3 sectors, you're bombarded by more instructions. So that you can see kind of the time in between these demands is decreasing. So the idea is can we derive the probability distribution of what's the probability that time is very small, let's say a few seconds. So we take trajectories, and in this case, track data from the Sherlock database, and we identify these heading changes, altitude changes, speed changes. And we don't count speeds if they happen at the same time as altitude. Sometimes speed changes just because you're changing altitude or heading. Then I showed last time we had done this analysis on a few sectors, arrival sectors in DFW, which was 1 day of analysis, included at the time only altitude and heading. And we kind of took one sector, single sectors in red. We took then pairs of sectors in blue and triplets in green. And we took one aircraft. If you're handling one aircraft sector, then you take this trajectory with that trajectory. So what if you're handling these two at the same time? And we combine their events, their turns and heading changes. What if I have 3 of them in 3 different sectors, and we combine their heading changes? And you see that the probability on a log scale here that the intertime is also good. So the value is higher for the 1 to 3 than 1 to 1. And we did it for en route sector, and also compared the two. So you see here, in the blue is for the arrivals, and the yellow is for en route, and because en route sectors are less busy than arrivals, you expect that the arrivals are going to be heavier. So the probability of having very small intermaneuver time for the arrival sectors will be higher. And that's what you see, the blue being higher than the yellow. Now, I showed this last time. What we've done since is we added speed changes. That analysis was only heading and altitude. We added speed changes. We also analyzed 7 days rather than 1 day. And because I wanted to publish this eventually, it gets published in the TM or paper, we want to report on the statistical significance of the data. And so we made an effort to analyze 7 days and see how do our statistics stabilize over this. And for some of them, we need to analyze a little bit more, so it's not completely done. But some, I will show you that we stabilized quite a bit. We did sensitivity to these thresholds, so we added this notion of attention, action, communication, and I'll show you that, and how these probabilities depend on that, and look at some trends. So I think this is in a better shape to be published as a chapter here, as an example of how we do modeling on the data. I think it's very relevant. It could be a separate white paper, as if we're doing a series of white papers. So you can see what we are gearing towards an actual publication from this as well. And let me just kind of run through this. So we talked to a couple of pilots, and we asked them what would be the changes in altitude, speed, heading that correspond to the pilot actually not needing to do it. So if we saw just a little drop in altitude, a little glitch in speed or heading, maybe that just requires the pilot to pay attention, but it didn't mean that there was an action that was taken. And then for this action, they told us it's 100 feet drop or rise, or maybe 5 knots or 1 degree change. That means the pilot will go in and make an actual thing. And for communication, if it's 1,000 feet, 10 knot, 5 degree or more, that means there was definitely a communication because you needed to coordinate that type of magnitude of the change. So we use these thresholds to kind of separate out. One thing, we went to Oakland for project purposes. We went from Texas to now we're analyzing the Bay Area and the Hollister region. So we're analyzing ZOA. And we picked these sectors, and you see here the daily the amount of aircraft minutes in them and the number of traffic. So some of them are busier than others. So we're hoping that the tool will be able to analyze everything, but we just pick these for examples to kind of capture a range of busyness in terms of sectors that are more busy, that have more aircraft minutes in them. You see in the high altitude sectors on the left, even though they have quite few aircraft minutes per day, the number of maneuvers is much less than the ones on the right for lower altitude. So about the same aircraft minutes, but a lot more maneuvering in the lower altitude as you would expect. Nadia provided me with this also to show that during nighttime, there's not much traffic. This analysis combined everything right now. We didn't do the nighttime by itself, in terms of average over everything. But just to make the point that it's not always busy same all times of day. So one next steps will be to really focus on more busy areas and such. But right now, this is sort of, so here, these are heat maps just if we use the threshold for attention versus action communication, you see how much the number of maneuvers there are. You see some areas, there's a lot of heading changes, altitude changes, and some much less. And you see it gets lighter for communication. So you see for attention, any little perturbation we're counting. For action, it's above 100 feet. And for communication, it has to be above 1,000 feet, for example. So you see it gets less and less. Let me see what's next here. Right. So in any case, so these are the plots. I showed you the probability of the intermaneuver time being less than the threshold for, again, attention, action, communication. And this is on a log scale again. And it's similar to what we saw for DFW, but you see as you go towards communication, for one-to-one, there's not much data. Not many communications when you were one-to-one that are very close to each other. So it goes kind of off the scale. But you see on the y-axis, so crossing around 10 to the -2, 10 to the -3. So there's 1 in 100, 1 in 1,000 chance of really communications being really close to each other. And of course, there's a as you go from attention to action to communication, there's less chance of things overlapping. So okay, so this is basically, it's almost it, because I'm just, okay, this is same on linear scale, I'll skip, and so this is, you see the for low altitude and high altitude as well. The plots are kind of busy, so. Okay, same story, so you can see how there's a lot more probability of action of the intermaneuvers being closer to each other to capture attention network to action and communication. I want to go to the trends. Okay, so in this one, you see over the 7 days, so there are 7 dots for each one of these. And so we're trying to see, as we add more days, our statistics stabilize. And you see it kind of becomes straight because of the low altitude. For the high altitude ones, there are less maneuvering, like I showed earlier, there's a lot less maneuvers. So I think we need more days for these to stabilize. But we're getting to a point where I think our statistics can be published, or at least we can publish and say, here's how confident we are with what we're putting out there. People can make their decisions. We're not. So just kind of to show you that we are readying this to publication. And this is the changes in the mean and the median between attention, action, communication. You can kind of see that the average intermaneuver time is about, goes from 50 seconds to maybe a few minutes if you are 1 to 3. But the blue is 1 to 1, so it goes down. The colors are changing. So you can see at the average or the median intercommunication time or intermaneuver time in general is much lower for 1 to 3. 1 to 2, that's what we expect. So basically, just recording on statistics, and this is basically the trends between attention, action, communication. So for again. 1 to 1, 1 to 2, 1 to 3. So as you go down, it's going to 1 to 3. Sorry, there's no legend on this one. But let's say if we take the 1 to the left, it's the probability that these things are less than 0.1 second apart. In the middle, less than 1 second, less than 5 seconds, less than 10 seconds, 20 seconds, 50 seconds. So this is basically a summary of the data that I'm just taking. So you see how on the y-axis what are these probabilities are and how they change as you go. Of course, less than 50 seconds, there's 7/10 chance that you get, on this scale, a communication that's maybe 50 seconds apart. But if you go to 10 seconds or 1 second, there's only basically, 15 in 1,000 chance that we're going to get an attention, or 5 in 1,000 chance that we're going to get a communication that's below 1 second. So this is starting to kind of.
Is there any way to tease out the performance implications of reducing the intervals?
Yeah, so how do you put this in a link there? Essentially, so if we reduce those, well, you want to increase the intervals, right?
Well, what I've struggled with a little bit with the analysis on intervention times is how do we account for near or simultaneous or nearly simultaneous events, right? We can look at sort of a Bayesian approach to characterize it. But then what is the implication of that for delays in performance or pilot workload or other aspects of things that we care about?
Like situation awareness as an example, because
right.
This is just looking at the time scale, and I'm going to use the word collisions the wrong way, but the collisions of events as opposed to what it takes to think what the human is going through to switch and deal with these other tasks.
So this type of analysis, we're looking at the actual data out there, is trying to tell us what would we expect? What do the pilots today see in the one-to-one situation, of course? And if we take the same type of behaviors, if aircraft did not change, and we put them in a situation looking at 2 aircraft at the same time, what do we expect to see? So setting a baseline, we have to remember that this is from trajectory data. So one of the steps I want to do is look at actual communication from audio, because these are naturally separated. You could get 2 communications at the same time. The maneuvers will be separated because of the time, And so by
But
correlating
that's
that.
measuring the physics of the decision-making, not the cognitive workload of the processes.
Yeah.
I think what
Yeah, I mean.
Jay was getting at. is-
Some implication.
Yeah.
Yeah, I mean, if you want to get to the cognitive side, you need a set of data that's actually monitoring, movement of eyeball and, some of these. And there are issues with that data as well. This is essentially looking at more kind of the end effect in the trajectories. How did all of these things materialize into the trajectories? And, the assumption that the system is safe today. So if we make the argument that we're not producing something that's different or more than this, the system should work in the same way and be seamless. But if we now want to go back to the human and the cognition and the effect on, that needs putting human in those conditions, which we don't have today, so we have to do human simulations and do those. But I guess the extrapolation that I'm trying to make here is that if the system, here's how the system looks like today, and if, for example, these probabilities are not different than what we would expect, than what they see today, there's no reason not to operate these things, at least for combinations of sectors where it's not busy and so on and so forth. That's really what this is kind of setting a baseline to say, how do things look in the data today? And
So your conclusion is different than what I'm coming to. I'm coming to the conclusion, this is not feasible.
well, so because we're taking sectors that are busy and we're combining things, so we're showing that it gets worse, of course, right? But now, if we do this analysis for sectors overnight, then you might get these probabilities really low. But these probabilities are significant. Still 1 in 100, 1 in 1,000. It's not 10 to the minus 9. And that's the point to make, is that we combine these just like today, you're going to get probabilities of that magnitude. So now, what are the implications of that? You can kind of take that, trace it to the 10 to the minus 9. And set that.
People have to remember your presentation when they hear my presentation after lunch.
Okay.
All right.
Sounds good. So I'm really, I mean, this is important because I would like to hear feedback on exactly your point. What are the implications of this and how do you use it? We're trying to set the baseline. What is in there in the traffic today? Of course, this is live our control.
It seems like the first two would be bonks, right? People can't do 0.1 in less than 1 second. Those first two, like if it was me air traffic, I'd bonk, right? You can't take it all in, but the 5 second and beyond is acceptable human performance. Is that what this is saying?
Well, this is basically this. It's basically saying what's important is the 0.1 second, less than second, because these are really close to each other. And you have
Same time.
Exactly. Yeah. Exactly. And that's why it doesn't happen for 1-to-1 today, because there's only one controller talking, it's not going to talk at the same time. But when you combine them, it may talk at the same time. So what's the probability of that happening? If it's very low, maybe you don't need to worry about it. But if it's high enough, you do need to worry about it. That's really the message.
behind
35% of the time, it's high.
And I see multiples. It's like 2 times more likely to happen with 3 to 1.
Exactly. So what's the trend? And then we go to 4 or 5. How does it trend? And that's why we want to kind of show you that dynamics. And we did kind of the Z test again just to see, do we trust these or not? And I'm done. I think that's really all. That's where we are, and I think we're close to. I think these are just back up slides.
Yeah, we'll have to talk about this a little more and how it ties to some of the other metrics and implications.
Absolutely. Yeah.
I think this is good.
Yeah. The way I'm seeing now is potentially an example of how you would do this kind of thing on the data that you use. And what's the baseline in today's environment? Cool. All right. So that's my.
Thank you. Okay, so that's the evaluation methodologies, white paper kind of status where we're at. We are going to jump now to Garrett Sadler and talk about the interventions, exceptions, What do you call it these days?
Interventions and exceptions?
Oh, okay.
Hi, thanks. Yeah, so I am presenting these slides on behalf of Andy Thurling, who is unable to be here. And so I will do my best to represent them. If there are questions, I will do my best to field those, but you may have to bear with me. I may not have all the answers for them, so I just have to bring them back to the group and report them out. So I'll do my best to both get us out of here by lunchtime and not tell you more than I know. So, so I guess if we put the slides up, or I control them from here. Okay, yeah, great. All right, so after the meeting we had in March last year, or no, this year, in DC, we got together to try to work on this methodology or tool that could be used to provide a quantitative estimate of the level of safety for a given end-to-end CONOP. And this tool takes in as inputs exceptions from system failures that come out of maybe a functional hazard assessment or an operational risk assessment and other elements of the environment. It's meant to be generally applicable, and it should allow to have some sensitivity analysis on changing the, say, M-to-N ratio or configuration, and could be used to potentially identify exceptions that you, if identify them, or if you address them differently, you could change the level of safety. And there's an example on that when we get into the vignette. This tool should be properly validated against some real-world operations, and then as sort of a stretch goal for it, we'd like to be able to input things like routes and weathers so that this could be used prior to going out on a day of doing some kind of operation. You can kind of get this, run this analysis ahead of it. And so we've produced a taxonomy, and I think from last year's November meeting, kind of were rather than looking at all the different use cases like we previously had, the realization was to dissect the exception rather than the whole scenario. We look at things not exclusively on relative to safety, but also sort of operational safety, like threats to the operation. And we then put these into this parameter table, and we'll see some of these parameter tables in a little bit. That could potentially, all those parameters could be ingested into some machine-readable format, where then it could be passed to some kind of prioritization scheme or queuing scheme that would stack them for service by the humans. And this is sort of like, rather than looking at M people to N aircraft, it's sort of like M people to an operation, M people to a situation. You know, what is the situation you're doing, rather than just the total number of aircraft that are in it. And so on progress, there is a graphics group that Marinaz has been leading, and she'll be showing us some of what they've produced here in a moment. We've also reviewed some ASTM standards, WK76044, that helps to provide a very detailed description of operational states you could have, and importantly for what for us here is transitions between states in aircraft system, and those transitions kind of identify where exceptions could occur. And this goes into that the parameter table that I mentioned, and so we've been filling out this parameter table using the vignette that Jay has provided. As a guide, we've had to go through that vignette and work on either clarifying or adding some assumptions to it, and clarifying or adding some details to the exceptions that come up. And what we want to do is eventually pass this into some queuing theories approach. And on the writing, the intention is to not have our own white paper, but is have this as a chapter in the white paper that's being produced. But as far as I'm aware, the status on the writing is that not really any has been done. So we'll need to, with the timeline that you mentioned by November.
That's his time. Yeah, there's no reason that these papers needed to necessarily be done at the same time, unless we were going to incorporate this one.
It may or may not need to be. I mean,
I
don't
think
want
we could just, maybe we'll just refer to it, you know, but into some pointers.
But as you can see there, we're still looking for somebody to volunteer leading the writing. So if there's anybody here, please either find me or if you know Andy, you could email him. So we have a lot of assumptions, and these are very text-heavy slides that I got from Andy. So a little bit of apologies for the text heaviness. But the assumptions that go into our analysis of the vignette are that the pilot doesn't have the capability to do like low-level flying. They're not controlling control surfaces. They're doing sort of goal-oriented, higher-level types of control and management. This is supposed to be agnostic to how the big O operator, that is like the company, it assigns responsibility to the aircraft or area. There also is this assumption that there is an established standard for service time or how long it takes to do things. Personally, my take on this assumption is that I think we should think of this rather than a standard time as a probability distribution of times that could represent some range of performance. This also assumes that there is some kind of strategy for queuing. So the queuing element is really very specific, I think, to the use case in the operation. And so to some extent, it kind of is a magical black box that we are feed into in this analysis, at least so far. These exceptions are assumed to be able to be broken down to a sufficient degree that you could decompose them to some level that is the appropriate level for addressing them with humans performing interventions. And we also make an assumption that's simplifying assumptions that the exceptions aren't interrupted while people are working on them. That is, when an exception occurs, they work the intervention from start to finish without interruptions there. This is meant to be an a priori analysis, so it can't really take in unknown unknowns, but the suggested solution for that is to add some safety buffers onto things. And we also make another simplifying assumption that the exceptions are more or less independent. There can be often interdependent exceptions that build on one another, but we are trying to avoid that confounding element, at least presently. Let's see, and some of these assumptions are a little redundant also, by the way. So this is meant for bounding severities and likelihoods of hazards. As I mentioned, the tool is supposed to be a priori. There is a suggestion of maybe taking that probability distribution I mentioned and performing modeling and simulation work that could be like a Monte Carlo simulation that helps see how sensitive things are to those unknown unknowns. Well, I'm not sure what the last assumption here on this slide is, but we can get into the rest of it, I think, without it. So I mentioned that ASTM standard, and what this WK 76044, my understanding of it, at least, is you obtain a really detailed description of an operation, including the personnel, the aircraft, and all the different states that those could be in. And what is highlighted on the slide here is, I think, the important bit that you get out of this practice, which is transitions between states. And those transitions, which could go from, say, normal to abnormal or emergency, those transitions are essentially like exceptions. And so we would have a list of exceptions that kind of come out of this, the guidance from this standard. So this kind of gives you an idea of conceptually how we're building out this tool. That the tool is, this box here that says Analyze Taxonomy. So we feed into it the output of a functional hazard assessment or operational risk assessment that goes into the ASTM autonomy framework. There may be elements of the environment that are fed into that. All of those things go then into this taxonomy where we build out this parameter table, and we'll go through the vignette and show you the parameter table, but it's essentially building out how much time do you have before you degrade the level of safety to certain degrees. That is passed to the queuing strategy, which then distributes tasks to be serviced by the humans. And I mentioned that we are looking at both, both looking at safety in terms of the safety to people and property, and also safety to sort of the operation and mission. So this table kind of shows different definitions of levels of safety. The two columns on that say safety on the left are more looking at safety for people and property, whereas on the right it's looking more on operation to the mission, and just sort of the monetary costs of degrading levels of safety.
And do you use the severity table to set priorities in the queuing?
Yes, one thing that's a little unclear to me, and I think some work needs to be done in the group, is to reconcile these definitions, because there are some differences between them. But the idea is to use the worst credible severity in analyzing things for the queuing strategy.
You're also, are you looking at urgency?
Yes.
In that as well, because that interacts pretty good.
Yeah. And so we'll actually see a little more about that. If Marinaz is still on, looks like she is.
I am, yes.
Yeah. So she put together this Miro board that graphically sort of shows what goes into our taxonomy and how we think of it. Like I mentioned, this is really looking at trying to define how much your time budget to certain degradations of levels of safety. And so actually, I think if I can hand this over to Marinaz, if she's able to sort of steal the presentation, is that something we could do, Jonathan?
Maybe
she has it on.
Maybe you can just drive the slide.
Then she can share the screen.
Yeah.
But right now.
Do you have my screen?
Yes.
We have it over there, yes.
Right now.
Okay. Yeah, because it's not in slides, it's online.
No worries.
Perfect. Okay.
All right, so yeah, take it away, Marinaz.
Okay, great. So I'm going to be walking the audience through how we are trying to demonstrate these exceptions that are coming in and how they are getting serviced. Before I start walking through the diagram, I want to kind of show some icons that we are using. So I'll start from here. These blocks that we are using show the severity of the exceptions that are coming in. So we have, for example, catastrophic that is being shown with like a red color, and then it goes to hazardous, major, minor, and minimal. And we kind of try to use these different colors to represent the severity of the exceptions. When you see a vertical kind of rectangle to show these exceptions, that means that the exception is coming in. And as I zoom in, you can see like these smaller blocks, square blocks within these vertical type of rectangles that we have here. And these squares are to represent time blocks, meaning that, for example, that an exception that is coming in a minor severity with like more time blocks, it means that there is like more time to get to that exception compared to an exception that comes in with less number of time blocks, meaning that it's more urgent and we do not have much time to get to it. Another thing to show in terms of the icons that we are using is that these blue blocks that you see that are horizontal are to represent servicing exceptions. So if an exception comes in and it's queued with our queuing algorithm, then we show that they get serviced when they are horizontal and the color changes to blue. Kind of to put it all together, going back to the diagram that we have, also sorry about a lot of scrolling, but I guess we have a vignette that we go through, and this diagram is based on that vignette. I try to zoom in from like here. From the left side, you can see that these exceptions are coming in. These are according to the vignette that we have. According to that, there is like two operators operating the drones for an inspection task. And the very first exception that happens is a battery exception. And from the left, you can see that this battery exception is coming in. It's at a major kind of a severity because a battery exception is important, but it's not catastrophic because we expect to have a safe landing option here. So the exception comes in, it gets distributed by our queuing algorithm, and according to the vignette, it gets assigned to the automation. So if I kind of right now zoom out, you can see that we have automation layers before things go to the operators, as you can see in the diagram. So according to the vignette, this battery exception comes in and the automation should be able to handle it. So the way we show it is that it comes in assigned to the first layer of the automation that you can see with the dashed line, and a safe landing is performed with this automation layer. And as I talked before, we show a servicing of the exceptions with the horizontal blue boxes. And we expect the safe landing goes as smoothly as we think, and there is a strategic rerouting for the rest of the drones according to this operation scenarios. And as this exception gets serviced, we show how the severity changes. For example, the exception came in at a very major severity level, but when it gets serviced by the automation, it goes to the minor severity. According to this vignette specifically, after safe landing or strategic rerouting for the rest of the drones, there needs an operational approval by an operator. So that's why we show these like dash boxes to show that this service is not complete. Instead, it gets assigned to an operator because it requires this approval, this final approval for a safe landing. And here we show that the exception gets assigned to the operator. Now, because just it requires approval, it's at a very minor severity level, and the operator has like a lot more time to get to it. But then here we show that if there needs an approval and a notification to the ground crew, it gets done, and the exception goes back to a safe level. But something we captured here, or according to this vignette, is that while the safe landing is getting processed by the automation, something happens, and that is that the return to base and safe landing cannot be performed because the battery is actually at a very critical level. So here we show that while that exception it's getting handled like according to the vignette, another exception comes up, which is that the return to base it cannot be performed. So we show it as a return to base exception. Now it comes in at a much higher level severity. As you can see, it's red, meaning that it's at a catastrophic level. It needs to be kind of assigned immediately. So this exception is assigned immediately to the operator because it requires, according to the vignette again, manual redirect to a safe area. And here we show that if the operator is required to do the manual redirect, they redirect the drone and not notify the ground crew. But again, based on this specific scenario, another exception comes up, which is that the manual redirect cannot be performed because the battery is at a very, very critical stage and it needs to land in place. Here, you can see it's still at a catastrophic level, but with a bit like less time blocks because it's very critical that an action is taken right now. So the automation takes it and performs a land in place as we are showing here. And then the operator is just required to notify the ground crew based on this latest exception. So if I kind of zoom out a little bit, you can see that for this battery exception, there is a journey that is happening at the top. You can follow that it came in at a major level, but it resulted in 2 catastrophic other exceptions that needed to be handled by the automation or the operator, and they are interdependencies between them. And also to follow up on the scenario, this is just one exception that kind of happened at the very beginning, but then as the operation goes on, there is this second exception that happens, which is the exception is that there is an intruder aircraft that comes in, and we show this exception again at a catastrophic level. And there are 2 operators, as we talked about. The intruder aircraft comes in, and the exception is assigned to both operators at the same time. So here we have the second operator showing in the diagram. If I zoom out, you can see that we had the operator 1 so far as I was zooming in. So we have 1 operator, and this is the second operator. And as the intruder aircraft comes in, both operators are notified at the same time. So here we are showing that that exception comes in and gets assigned in parallel to the both operators. But as you can see, one of them has a catastrophic kind of major severity coming in compared to the second operator that has a major severity. The reason for that is that according to the vignette or the scenario, the intruder aircraft is closer to the geofencing of operator 1 compared to operator 2, and it affects more of the drones that the operator 1 is covering. So it's really more timely for operator 1 to take an action. And how we show that difference is with the severity colors to show that for operator 1 is a more timely exception compared to operator 2, who has more time and is a little bit further than where the intruder aircraft is coming in. So we assign the exceptions, which requires like redefining their drone routes because of the affected area. They both define their affected area, and after they do that, they kind of, if you follow the arrows, it gets assigned to the automation layer for automated dispatch after the intruder aircraft clears the area. So this is the, I can again zoom out to like show the diagram again at a high level. The top box is the exception 1 journey with the battery exception. The bottom box is the exception 2 journey with the intruder aircraft, and everything is according to a time from left to right and how things are progressing. And this is specifically for the vignette that we have, but feel free to let me know if there are questions with regards to the diagram.
Yeah, it probably would have helped to review the vignette prior to this, so I apologize for that, and I apologize, Marinaz. But thank you very much for taking us through that. I think with the time that we have, I'd like to review some of that a vignette so that we can go into the parameter tables that I had mentioned. So yeah, thank you, Marinaz. And
sure.
Thanks. All right. And does this no longer work? No problem. Oh, there we go. Yeah. Okay. So the vignette that was produced is, how many people has everybody been familiarized with this vignette? People read it before? No? Okay. Well, there are, it's essentially a wildland wildfire kind of mapping mission. It's not that there isn't an active fire, but these drones are out surveying a wooded area to identify potential spots where fires could break out. And there are two sort of exception events that come up, which Marinaz was taking us through. One of those is a battery anomaly that then has subsequent exceptions within it. And then the other is a detect and avoid intruder aircraft that sort of flies through the area. As I mentioned, we had to go through and add some assumptions to this. In the interest of time, I might just jump into the vignette and we can go back to these and I can send out what all these lists of assumptions are. So we start, and this is, oh, I'm looking at the wrong thing.
I think we should maybe also take a quick step back and talk about why we're talking about the exceptions so much. In the Langley meeting that we had, we've always called this the end-to-end working group, right? And it's like the number of vehicles is a big driver. But we never really believed that it was just the number of vehicles. We always believed it had to be with the interface, how often you have to interact with it, etc. Mark presented some work that Wing's been doing, where they just give strategic commands for areas that have nothing to do with the number of vehicles that are in there. And so it makes the end-to-end sort of a misnomer. That's not really what we're worrying about. But we believe that the metrics that we've been developing will work for either of these cases, whether or not it's, whatever the workload driver is, if it's the airspace or if it's the number of vehicles or, whatever is the actual workload driver. But we needed to start to characterize those exceptions. And so our group worked on developing the metrics that should work in any of those cases. And we wanted to characterize some of the metrics, and we developed a little snippet scenario that we could use as an example in both of the groups to explain what we've been doing and why we've been doing. So I put together a really simple one and handed it over, and now it bears no resemblance to what I did anymore. And so we need to go back and revisit it from our side, but that's why this snippet is important. That's why the exceptions and the interventions are important, because that's really what's driving the workload and the number of vehicles that could be controlled, or the number or the area that could be controlled.
Thank you, Jay. Yeah. So as I mentioned, this is sort of a area in Northern California. This company, Drones R Us, has contracted with CAL FIRE, and they're using sensors to identify these kind of hotspots. So they're out in an area that is over both homes and buildings, roads, trails, and obviously wooded areas. So there's people on the ground, there's infrastructure down there as well. Each operator, each one of the humans, of which there are 5, is overseeing 10 aircraft. So there's a sort of a 5 to 50 ratio, or each of them on a 1 to 10 configuration. And as they're performing this survey, then we have an operator who gets alerted that there's a battery anomaly. And then this drone starts to automatically select and start returning to base. That's what it decides to do. The UTM system that's in place, which is one of the assumptions of this, that prior to the mission, there's strategic separation provided by a UTM system. UTM looks at this return to base thing and evaluates it as okay with the operational volumes that are there. And the operator reviews and approves of this solution for it to come back to home. But as it's progressing there, I'm skipping ahead, the operator also radios the ground crew, potentially that there might be an emergency landing that gets performed because of this battery issue. And lo and behold, they get a new alert that the battery has gone to a critical state. It's insufficient for returning to base. And so then there is the operator redirecting it to a predefined safe zone that is free of homes and people and structures. And radios the ground crew that, okay, it is going to have to do an emergency landing and it's going to be over here. As that is happening, there is yet another exception that comes up where the drone isn't going to be able to make it to that safe landing zone and it needs to land immediately. And so the operator then radios to the ground crew to let them know that this thing's going down about this area to go get it. So that's one of the exceptions, and that was that first journey, as Marinaz called it, that she was breaking down in the diagram. The second, and a nearby asset also is then tasked to kind of watch the emergency landing as well. After this, they go back to performing their survey mission. And then our second exception occurs where there is an intruder who flies through the area, and this is going to pass through the working area of two of our human operators. They have their drones working in some geo-fenced area, but this produces some DAA alerting. And the way of resolving this is the operator kind of draws a new keep out zone for their aircraft that will say, proceed outside of this area, don't go in here. And the aircraft that have a conflict then move outside of those rectangles that they drew on the map and to their safe zones, and the intruder aircraft then flies through. And afterwards, those vehicles then are put back on their mission. So I think that is the vignette. And I mentioned the parameter tables then. So this is sort of the meat of what we have been working on. So is it cut off a little bit? No, it's just hard to see from here. So on the left-hand side, there are some of these parameters that we defined, which include severity, safety priority, mission priority, the time budget that you have to degrading to a minor level of severity, and then you also have these other time to a major level of severity, time to hazardous, time to catastrophic. Service time is in here. I think it probably should be, as I mentioned, a probability distribution rather than a single value. The resolved severity, meaning, when you recover the situation, what is the best possible recovery level you could get to? You might not be able to go to no safety effect. You might only recover to something that is more like a minor or major level of safety. And then you also have the time to get to those recoveries. And at the bottom, we have also our neglect time, which is defined a little bit differently than it has been mentioned in previous groups. I think we don't even use neglect time as a term anymore. But what is meant by this is actually the time from the exception onset to servicing it. And that's what is meant in this context. And so for the DAA event, we've been able to sort of fill in this parameter table Unfortunately, I was not at the last IME meeting, so I wasn't there when some of these values were filled in. But if anybody was there, maybe they can help us go through the rationale. But looking at this with the DAA event, we have that the worst credible severity is at a hazardous level. This safety and mission priority, these get assigned values from 1 to 10, I think, for safety priority, and the mission priority is a little confusing to me because it goes like from 4 to 7. I think these are related to the time blocks that Marinaz was talking about. But this is a high safety priority. Needs with the intruder aircraft needs to be worked basically immediately. And so then you see the time to minor is 0. It surpasses that. The time to say major would be if you get to like a loss of well clear. And one of the reasons we were able to fill in this table also is the DAA event is a little more tractable because there has been a lot of work on DAA, and in particular the timeline for alerting and response. And so that's why, yeah, we were able to fill in some of these. So that 40 seconds to say a loss of well clear, that's sort of the approximate timeline from say a caution level alert to loss of well clear. The time to go into the hazardous severity of NMAC is 70 seconds. Here it says for the catastrophic severity that is not applicable. And so this was something I had a question about. I was curious as to why that this catastrophic level was seen as not a credible outcome. I mean, it's challenging to run into a small UAS, but it's not impossible. So I don't know that. So yeah, if there's anybody who knows the rationale, let us know. The service time was, I think, taken as 10 seconds, which is maybe approximately about how long it takes to draw the rectangle and get those aircraft starting to move. And the resolved safety severity for this, you could go all the way to no safety effects. So, you know, if you perform the avoidance maneuver for the intruder, and then go back on mission, you essentially return to the system to not having a safety effect. The time then for recoveries are listed as 45 seconds of time for those drones to make their way out of that keep out box that was drawn. And the neglect time, we have here as 0 because you really need to immediately pay attention to this. There are other parameters. This table was too large to fit on one slide. So, you know, you have a time to verify, have other members sort of verify the solution. In this case, this is 0. You're not going to look for another operator to verify your solution before doing the avoidance maneuver. If you need a specific resource to do this, you do not need some sort of special resource for that. The recognition time to see the problem, we put as 2 seconds for this. For the environmental severity, and in this we're assuming the environment, we assume that the environment as well as things in the phase of flight are handled upstream of this point in the analysis. So I guess we are saying not applicable for environmental severity. And for this, we're also not really doing the queuing thing because you have one exception and you're doing it immediately. It's a queue of 1. And operator bandwidth, this is a metric that I think really comes from the big O operator on that. So that's what I've been referring to when we have our taxonomy and parameter table. The taxonomy is looking at the degradation of levels of safety as defined by these time budgets. And these then filling in the parameter table is sort of this piece of analysis. So
and you've done that for 2 exceptions?
That's you provided a great transition. We've done it for one. So, yeah, the DAA event was seen as more tractable just because there's been a lot more work on the alerting timeline. We're familiar with that work, the UASNS project. So with the battery anomaly, yeah, this has been an ongoing piece of discussion on sort of how to fill out this parameter table because it's not as obvious there. But that's sort of the status of things that we have so far is we've developed this taxonomy of looking at an exception, breaking it down into the time budget to degrading the level of safety. And that's where we are. And so the next steps are really to start writing, because as I believe there really hasn't been writing started on this part. And yeah, so I can try to take any questions.
Well,
I may not have all the
do you guys have any timeline estimate for when we might have a draft?
I'm not aware of one, but I think I can get with Andy to get you something soon.
That's something we should probably try to get some feel for.
Yeah.
What is safety degradation? What are the units? Is it an arbitrary scale or?
I think it's more or less an arbitrary scale.
Do you have a definition, like a rubric or something? So
We
1, 2,
do,
3, 4,
and
5.
it's going, so that really big table that had like the columns of different definitions of severity levels.
One of those.
Yeah,
Another one. So severity and safety, right?
Yes,
I acknowledge, yeah.
Yeah.
That's the only way, you have to define it yourself.
Yeah, and so I think as I mentioned before, there it is. I think we really need to do some reconciliation between these different definitions for safety and severity, because they are different, and there is some arbitrary degree to them. But yeah. Yes.
So I have a question about when you have a failure scenario on the battery. So you have a 5 to 50, so 1 to 10, let's say. So this one operator under whose region this drone failed, they have to disengage from the other 9 to take care of this exception for one drone.
Yeah.
So I don't think I saw anything about the re-engagement time with the rest of the 9.
Yeah, I think that is wrapped into the time, so we have these time to recover to different severity levels. And so I think some of that re-engagement and reassignment of those other vehicles would be in that time to go back to the sort of nominal level. But if not, then we do probably need some like follow-up service times that are, a consequence of what happened in the exception. Thank you. Nelson.
I wonder if have you given any thought to like flowing things backwards to find requirements for like a detect and avoid of an uncooperative, like that's a question I think for detect and avoid is like what range, what reliability, things like that. Does this flow back that way?
So some of that would come from, potentially some things would come out of a functional hazard assessment and operational risk assessment, I think. But yeah, the DAA event is nice to decompose because it does break down, there's our standards written for it, and you do have a nice like alerting timeline, so it's easier to look at.
I don't want to be too specific on that case, but like in more like component reliability for the battery or something like that. Does this help you define how much to invest in mitigating these things ahead of time so you don't overwhelm the human?
Well, I think, part of what you can do, maybe not that specific, exception, but I think you can use this kind of analysis to say, we can only have this many exceptions in this time period, right? you know, however you as an, you know, manufacturer get to there, we don't care. And, you know, and there's a lot of simplifying assumptions, saying something like that. But I think that helps you get to that sort of analysis.
But to fill out the parameter table, yeah, you do need to reach back to, you know, whatever literature would provide some of those parameters.
Mill standards.
But yeah, it's not necessarily from one specific source.
Great, other questions?
I just had a question about how this would scale, like, would you do this for every function or?
That's a question I have as well. You know, if you go through and, you know, take some elaboration of all those different states the system could be in and then transitions for them, I think to properly do this, you would go through comprehensively and do that, but it would be a lot of work to do. I think you'd have to maybe set things up where you could input the parameters for your operation.
Yeah, although with the level of autonomy on some of these aircraft that we're looking at, the solution space is pretty small for operators, right? They only can do 3 or 4 things, and so, you know, if all of these exceptions are leading you to an, you know, land now scenario, then you know it simplifies things.
Yeah,
On the parameters and the values of the parameters, so some of these for the DNA available because there was some human to do like this studies that.
Right. I think that's where they get some of those.
Right.
That's
And
yeah.
for the other DNA, people to study.
Yes.
You speak to sometimes think about the relationship between the simulation and I spoke about. You need these parameters to feed in to do it. Can the simulation be used to derive parameters? Or you have to go back to human?
Sort of like recursively, or?
Yeah, can this setup be used to actually derive parameters? So let's say the 40-second.
Yeah.
You know,
I don't know if the models are veridical and validated enough to be able to really produce those kind of results that we believe.
So how can we use these models then? So let's say we do human do flight tests.
Well, I think we need to get some of that data from some manufacturers. Some people are flying, you know, and they have data on, you know, how often these things occur and how long it takes to deal with them. Maybe not all in that kind of format. It's not data that is easily, readily shareable by operators for obvious reasons, and so it becomes a little more difficult. So I think you have to do some stuff in man-in-the-loop simulation, and use that data and make some assumptions.
Yeah, I'm always curious about how these fast time type models can really help.
Well, and I think they could, like going sort of to what the question that Nelson had, like the source from where you get these, you know, values of the parameters is not specific. It really could come, I think, from whatever source, and if you do have good modeling, it could lend to that too. But, you know,
you do sensitivity analysis. Right? You know, you could look at a range of values and look at which ones could be more.
I think another point, the idea behind this is that it's incredibly specific to your operation. It's not really like generalizable. So you're looking at specific operations with your setup, your vehicle, your people, and focusing on that. So really, you do have to do something, right? Like the FHA. That's what we're talking about. It all comes from that. You have to do a lot of this analysis anyway. Maybe not all these parameters, but from that initial analysis, you can hopefully derive some rough estimates for these parameters.
Yeah, so it does assume a pretty comprehensive set of inputs coming from that.
What you gotta do.
Yeah.
As you did more scenarios, you would find patterns and say, you know, land now, it's going to happen. This is our common output. That's what for a number of different scenarios.
Right.
It just takes time to get it done. You know, not many people are flying end to end, so you almost need you need a simulator, right? Or for the companies who are flying to be motivated to do this.
Right, and provide the data in some sanitized form. Yeah. All right, anything else? All right.
No, sorry. I know people are hungry. But there's a difference between an exception that requires human intervention and an exception that is automatically addressed. And, you know, I think that's part of what the ASTM standard practice is addressing is where is it a triggering event that now requires the human to be involved in the decisions versus there may not be a triggering, there may be a trigger for an exception that doesn't require human intervention.
Yeah, and I think that is not a generic answer, right? That is a very specific
It's a
interface
specific,
design
yeah.
answer, so that's hard.
But that's what
But understanding that those exist.
But the framework that the standard practice is trying to address is to help you with those, you know, you look at all the functions that are being done and the role of the human and the role of the automation and triggering events that change the role of the human and the automation, that requires now the human to be part of executing that function. And that, by the way, you called it a standard. It is not a standard yet. It is in the process.
It's in the balloting process.
Right, it's like watching how a bill becomes a law from school, but it is still going through that process.
Okay. All right, thanks. Thanks very much.
Thank you.
So